6 problems from spring 2024. Let's get it done. All right, number 1. Transform the equations 2r equals z and z equals 2 plus square root 1 minus r squared from cylindrical coordinates to Cartesian coordinates. What surfaces do these equations represent? All right, now cylindrical is polar plus z. So we're like, okay, so we just have to remember polar. Now the good thing is, polar, you have 3 things. X equals r cosine theta, y equals r sine theta. But we have no sines or cosines. No, nothing like that. We just have r's. So we say, oh, well, r squared, that's x squared plus y squared. Okay, so that's what we have to remember. Or we can say, hey, that's the same as saying z equals 2r. That will become what? Z equals 2 square root x squared plus y squared. All right, there we go. There's one equation. Now, what about this other one? Z equals 2 plus square root 1 minus r squared. Well, we have to work around with this a little bit. So what do we say? Well, z equals 2 plus the square root 1 minus x squared plus y squared. All right, well, that's kind of right, but maybe it's not too compelling. So we can say, all right, well, let's see, what's another way to write this? I will say, I like this, by the way, but I want to get some insight into what it is. Z minus 2 is the square root 1 minus x squared plus y squared, and square both sides. Z minus 2 squared equals 1 minus x squared plus y squared, or x squared plus y squared plus z minus 2 squared equals 1. That's a sphere, right? If you see something squared plus something squared plus something squared, sphere. And we say, okay, where's the center? Well, the center, it's at 0, 0, 2, and the radius is 1. Okay, now you might say, great, so is this the same as that? So here's where we're getting into technicalities. No. What's the difference between these two? Well, the difference here is, notice what z. Z is always 2 plus something. So it's 2 and above. This says, oh, I don't have any restriction. So what's happening is that once we square it, we kind of lost some information. And so that's why you have to be careful when you're squaring. So this surface right here is a sphere, the whole sphere. Whereas this surface over here is not the whole sphere, but the top half of the sphere. It's a hemisphere. So this is a hemisphere. Now, what about this one here? Z equals 2 squared of x squared plus y squared. Well, that is a cone. So we say, okay, great, cone. All right. So that's part A. Cone, hemisphere. Now, say, okay, well, what's the volume of the region described by the inequalities? Well, we know the shapes. We say, okay, cone and hemisphere. And, all right, so if we think about what's going on, we have a cone coming up, and then it's going to be topped off by a hemisphere. And we say, okay, so we have half a sphere, and then down here we have a cone. All right, so now we just need to figure out what are the volumes of these shapes. So let's start with a half a sphere. We need to figure out what's our radius. Well, we know what our radius is. Our radius is 1. And for the volume of a sphere, well, that's 4/3 pi r cubed. So if I have half a sphere of radius 1, then this part right here will be 1/2 times 4/3 pi times 1 cubed. All right, so that's our top piece. Now, our bottom piece, our cone. Well, what's the volume of a cone? Well, the volume of a cone is 1/3 pi r squared h. It's basically 1/3 base height. So the height here, how high up do we go? Well, we go 2 up. And what's our base? Well, our base is the same as our radius. So r is 1. So we say, okay, so this is what? Well, it's going to be 1/3 pi 1 squared times 2. All right, good, good. Now, what's left? Well, we have 2/3 pi. We have 2/3 pi. We add them up, and we get that the total volume is 4/3 pi. And there we go. All right, so it's finding volume. Cool. All right, on to number 2. Okay, matching. Choose the correct equation from A to G on the right for each surface on the left and write it in the box. Now you may say, okay, hold on, there's 1, 2, 3, 4, 5. Here there's 1, 2, 3, 4, 5, 6, 7. So there's more equations. So we're not going to use them all. So we kind of have to figure out what kind of equations they are. And we have to be careful with these pictures. It can be a little bit tricky. But let's take a look. Now here, this one needs to be a hyperboloid of 2 sheets. Because it's the only part that's disconnected. And so we have these 2 pieces coming out. All right, so when we're looking for a hyperboloid of 2 sheets, well, there's certain combinations that we're looking for. But notice here, there's something that's pretty nice. Namely, if you slice, so you take this slice here, this slice x equals 0, we should have no solutions. Which means if I cover up the x term, there should be no solutions. Well, I can see solutions, I can see solutions, I can see solutions. Yeah, I can make that work. How about here? Yeah, I can make that work. Yeah, that seems good. How about here? Minus, minus, comes a positive? No way. So that has to be G. All right, slices, by the way, great way to narrow things down. Slices and shapes. Okay, so what do we have here? Well, here we have the cone. So you say, perfect, we're looking for a cone. Now, what do cones look like? Well, essentially, they look like x squared plus y squared equals z squared with some constants thrown around for fun. So there's no, I can put 2x squared or 4y squared, but it's x squared and y squared and z squared. That's it. And okay, so great. So I'm looking for things that look like that. Well, that has a 1. Nope, that term's not squared. There's a 1 there. There's a constant there. That term's not squared. I've already accounted for it. But that has everything that we could want. An x squared, a y squared, move it across, you get a z squared. Life is good. So, A. All right. Now, next up, what do we see? Well, this is a bowl turned sideways. Or, if you like, it's a paraboloid. But a bowl is easier to remember, and definitely a lot easier to spell. Okay, so we're looking for a bowl. So we're going to have something not being squared. And now in particular, see how it's opening in the direction of the y-axis? So that says I want y equals something x squared, something z squared. So I'm looking for a y equals somewhere. And I see here, I have a y equals. Now here, this is also, I have something that's not squared, but it's a z, not a y. And here, you have one being added, one being subtracted. We want them both the same sign because we get a bowl that way. So that's our option. So C, G, A, C. All right, now the next one. Ooh, what is that? It's a Pringle, right? Wait, Pringle? That's not one of our shapes. No, it's not one of our shapes. But what we see is this is a saddle. Okay, so what's a saddle? Also knowing it's another type of paraboloid, but you get parabolas going one way, and then in the other direction you get parabolas going the other way. So we're looking for, one thing that's not being squared, and the other one is a plus square and a minus is squared. Now we already talked about, this was the other place where we could see parabolas, and notice how we have z is a positive thing squared and a negative thing squared. So that must go there. G, A, C, F. Now, our last thing. Oh, cool. What do we see? Well, it looks like a circle that's been copied up and down. This is a cylinder. So you say, okay, how do you know a cylinder's? Well, you're missing a variable. And in particular, you're always seeing the same thing with z. So I want something without z. See, there's a z, 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 there's a z. So this one doesn't have the z. That's the giveaway. G, A, C, F, B. Nice! That one's done. Okay, next problem. Find a vector perpendicular to the plane containing the points minus 1, 0, minus 1, 2, 4, minus 1, 2, 4, 4. Okay, now we know vector perpendicular to the plane, they are just trying to say normal with the long way. So we're looking for the normal vector. Now what do we know? Well, we know the normal vector has to be perpendicular to vectors in the plane. So we say, okay, cool. We just have to find some vectors in our plane, and if we can find enough vectors in our plane, then we can construct something that's perpendicular. So we start by marking some points. Minus 1, 0, minus 1. 2, 4, minus 1. 2, 4, 4. And we're going to mark some vectors. So we pull two vectors in our plane. All right, so what are they? Well, minus 1 to 2 is 3. 0 to 4, 4. Minus 1 to minus 1, 0. The other one, minus 1 to 2 is 3. 0 to 4 is 4. Minus 1 to 4 is 5. 3, 4, 0, 3, 4, 5. All right, great. Now, what do? Cross. You want to find something perpendicular to both. All right, well, okay, so here we go. Set up the matrix, I, J, K, 3, 4, 0, 3, 4, 5, and go diagonals. I times 4 times 5 is 20I. J times 0 times 3, 0J. K times 3 times 4 is 12K. Other direction, 3 times 4 times K, 12K, but subtract it. 4 times 0 times I, 0I, but you subtract it. 5 times 3 times J is 15J, but you subtract it. And so, what do we end up with? We end up with the vector 20, negative 15, and 0. Okay, so that is the vector we can use. Now, we can also pull out a 5 if we wanted to. So, for instance, we could say, oh, this is the same as 5, because 5 is a common factor, for negative 3, 0. And then we could just choose this part here. These are both correct. Normals are not unique. In fact, there's infinitely many normals you can always scale. Now, part B, 2 points. Find the area of the triangle formed by the above 3 points. So it's like, oh, hey, we want this area. Well, how do you find area of triangles? Well, the answer is cross product. The same tool that we used to make our normal also comes in handy. So we have that the area of a parallelogram, not a triangle, but a parallelogram, that's the magnitude of u cross v. So the area of a triangle, well, the punchline is that's 1/2 a parallelogram, so that's 1/2 the cross product. So for our case, we say, okay, it's 1/2 of the magnitude of this. Well, we can pull out the 5, and so it's 1/2 magnitude of 5 for negative 3, 0. Now the 5 just goes out, 5 halves, and then take the magnitude, square root of 4 squared, negative 3 squared, and 0 squared. Well, 16 plus 9 is 25, and so we say, okay, 5 halves, square root of 25, which is 5, so that's 5 halves times 5, that's 25 halves. And there we go. All right, so that's the area of the triangle. Now, what's our last part? Find the angle between PQ and PR. Okay, so we have to find an angle. Now, how do we find it? Well, technically, what we should do, and I will point out that whoever wrote this has to be careful here. You don't know a priori that the angle is between 0 and pi halves. What they're trying to do is they're trying to get you to use the fact that there's a sine of theta. The problem is it could be an obtuse angle. And so when you're finding an angle between vectors, you can't use the sine because you can't know if it's an acute or obtuse angle. So what do you use? The cosine. So we're going cosine here. All right, so what's cosine have to do with it? The classic question. What's cosine got to do with it? Got to do with it? What's cosine but a special way of measuring stuff? Okay, so we have u dot v is equal to magnitude of u, magnitude of v, cosine theta. Where, if you look, this was our point P, and then we had our point Q and our point R. So PQ was that vector. PR is that vector. So we say, cool. So we have our PQ and our PR. We'll have it there on the screen there. And so we say, okay, so what we're going to do is we're going to take 3, 4, 0, cross 3, 4, 5. And that's got to be equal to the magnitude of 3, 4, 0 times the magnitude 3, 4, 5 times cosine theta. All right. Now, 3, 4, 0, sorry, not dot, cross, sorry, dot. I know how to copy. Well, sometimes. Okay, so the dot product, you get 9 plus 16 plus 0 equals, here, it's the square root of 9 plus 16 plus 0. And here, it's the square root of 9 plus 16 plus 25. All right. So we get 25 is equal to square root of 25 times the square root of 50. Now, if you think about it, square root of 25, don't forget the cosine theta, is 5. Square root of 50, that's 5 times square root of 2, cosine theta. Or, if you divide, you get, oh, cosine theta, 25 divided by 25 goes away. That's 1 over root 2. So we're looking for an angle from 0 to pi, technically speaking. But now, because we see that cosine is positive, it will be in the first quadrant. So we're looking for an angle where the cosine of that angle is 1 over root 2. That's actually a number that we know. In fact, this is the same as cosine theta is root 2 over 2. The angle that does that is pi over 4. It's one of those ones that we have memorized. Because, of course, we all love trig, right? Of course we do. That's so cool. Trig, it's the best. All right, well, that was number 3. Number 4. Find the parametric equations of the straight line that is perpendicular to the yz plane and that passes through the point A 2, minus 1, 3. Okay, so let's just quickly remind ourselves what's going on here. We have our x, y, z. Now, what is the yz plane? Well, it's the plane that's formed involving y and z. Okay, so that's our yz plane. How can you be perpendicular to the yz plane? Well, you can be perpendicular to it if you're doing what? You're moving purely in the x direction. So the normal to the yz plane is the vector 1, 0, 0. Now, why do we talk about the normal to the plane? We want the line to be perpendicular to the plane, so the direction of the line has to be perpendicular to the plane, which means it has to be a multiple of the normal vector. So this is the direction of our line. And so now we say, cool. We quickly scan and say, which way do they want us to write the line? And they say parametric. And then we're like, really cool, because that makes life easy. So you have x equals y equals z equals. And then we write down our point, 2 minus 1, 3. And then we add 1 times t, 0 times t, 0 times t. Right, where this part right here, this is our point, 1, 0, 0. This is our direction. And so this simplifies down to saying x equals 2 plus t, y equals negative 1, z equals 3. And there's the answer. That's the line perpendicular to the yz plane, and it passes through the point 2 minus 1, 3. All right, now find the distance from the point 1 minus 1, 1 to the plane x minus 2y plus 2z equals 0. Give your final answer as an integer or a fully reduced fraction. Whoo, okay, neato. Now, we can do this in a couple of ways. So we're looking for a distance from point to plane. One way we can do this, and by the way, part A, nothing to do with part B. So this is one of the problems where they're like, oh, I want to test on a couple of ideas. So they gave us too many problems. So that's why part A, if it seems suspiciously easy, because it was. So part B will seem suspiciously not easy. That's why it's worth a lot more points. So we can either do the following steps. We say, look, we have our point, we have our plane. So we can, if we were so inclined, say, hey, you know what? We also have, if we have our plane, we have our normal vector. And what we can do is we can use that to make a line. We say, okay, great. Use the normal vector plus the point to make a line, and then you find the intersection point. So, because you can find the intersection of a line and a plane, and then you can find the distance. All right, that's one way to do it. The other way to do it is to remember there's a kind of a cool formula. And here's what it says. So if you have ax plus by plus cz equals d, okay, so there's our plane, and you have a point x0, y0, z0, what you do is you plug in. So you have ax0 plus by0 plus cz0, subtract d, take the absolute value of that, and divide that by the magnitude of your normal, which is a squared plus b squared plus c squared. So this is, downstairs is the magnitude of the normal. So essentially it's like you plug in the point upstairs where you've shoved everything on one side, take the absolute value, and downstairs you take the magnitude of the normal. So we say, okay, let's throw that in. So here we go. So according to the rule, we're just going to go through. We're going to have 1, because I'm putting in x equals 1, minus 2 times minus 1, plus 2 times 1, minus 0, so I'm just minus d, because I want to make sure I don't forget to account for that, square root of, now coefficients, 1 squared plus minus 2 squared plus 2 squared. All right, well, upstairs you get 1 plus 2 plus 2, which is 5. Downstairs, 1 plus 4, which is 9, square root of that. Well, that's 5 over 3. There you go. So knowing your formulas, it's a great help. In fact, it makes the problems a lot easier, right? Of course it does. That's why we memorize all our formulas. Yeah! All right. Well, that was number 4. Okay. Number 5. An archer stands on the ground at A00, 20 meters away from the foot of a wall. Okay, so archer, that's the A. Wall, they didn't mark it, but that's okay. Diagram, by the way, not to scale. She aims an arrow straight at the target. There's the target. Mounted on the wall at T2020. 20 meters higher than the arrow's initial position. Okay, so this is up by 20. So we're going to mark here 20. Mark here 20. Okay. The arrow is shot with an initial speed of 30 meters per second. downward acceleration due to gravity is 10 meters per second squared. What is the position of the arrow after t seconds while in flight? Now, notice that this is 0, 0. So let's figure out a couple of things. We know acceleration. And in particular, we're going to assume that this behaves like the normal acceleration. In other words, the acceleration is constant, pulling things down. We only have two dimensions, so acceleration looks like 0 minus 10. We might say, wait, you got it wrong, Steve. It says 10. Downward. So downward says, oh, you're going in the down direction, so that's a minus sign. Now, that's A of t. Let's now do V of t. Well, we're trying to get position, right? So acceleration, velocity, position. So velocity. We're going to say velocity is, well, 0, integral 0 is 0 plus a constant. And then we have, oh, negative 10t plus a constant. Now, we have to stop and say, but wait, what is velocity? Now, that's the fun part. What do we know about velocity? Well, velocity, we actually have two pieces of information. We have a speed, and notice they say speed, that's going to be an important word, and we have a direction. Okay, so every vector is a combination of magnitude and direction. So the speed, that's our magnitude. Okay, so magnitude. Cool. What's our direction? Well, now we have to say, well, look, what's the vector that points from here to there? Well, it's the vector, you go over 20, go up 20, it's the vector 20, 20. But of course, if I care about direction, I want to make it into a unit vector. Well, first thing, let's just scale it to be something simple like 1, 1. Say, okay, great. Now, is that a unit vector? No, because the magnitude's wrong. What is the magnitude of this? Well, it's 1 squared plus 1 squared is 2 square root of that. So what you'll do is you'll take 1, 1 and divide by root 2. And so that's the unit vector direction. Okay, great. So in particular, the velocity at time 0 is, multiply this through, and by the way, square root of 2 is the same as square root of 2 divided by 2, right, because this is 1 over square root of 2. So you'll end up with 15 root 2 comma 15 root 2. And in case you're like, whoa, wait, hold on, Steve, slow down. I know you like going fast, but maybe slow down this time. So you have that 30 over root 2 times by root 2 over root 2. Root 2 times root 2 is 2. 30 over 2 is 15. So that's where they get 15 root 2. Okay, so how do we use that? Well, that's our velocity at time 0. But notice we have velocity at time t in terms of this expression. We just have to find a and b. So velocity at time 0, well, that's going to be 15 root 2 comma 15 root 2, which is a, b. So now we have a and b. So our velocity at time t is 15 root 2 comma minus 10t plus 15 root 2. Okay, whew, nice. Now, we've gotten velocity. Start with acceleration. We got velocity. What comes next? Position. Oh yeah, gonna do position. So how do you get to position? You integrate. Okay, so our position, which is r of t. So we use r of t for position. That's 15 root 2 times t, comma, minus 5t squared, plus 50, I forgot the constants. 15 root 2t plus a constant, comma, minus 5 t squared plus 15 root 2 t plus a constant. But now we know where we are at time 0. So we have that r of 0 is 0, 0. But if you plug in 0 and 0, that gives you c, d. So these constants c and d are 0. So we say, okay, so that says our r of t is 15 root 2 times t, comma, minus 5t squared plus 15 root 2 times t. And there we go. All right. We found our position. Nice! Now, part B. How far below the target does the arrow actually hit the wall? Okay, so it's like, where is that? All right, so let's see. Well, where will it hit? So we need to figure a couple things out. First off, when do we know we hit the wall? We'll hit the wall when our x of t is 20. Okay, so this is our x of t. X of t. So let's solve for that. So we have 15 root 2 times t equals 20, or t equals 20 over 15 root 2. Now, we can times by root 2 over root 2, if we like, and we do. Root 2 times root 2 is 2, times 15 is 30. So you have 20 over 30, which makes 2/3 root 2. So that's how long it takes for the arrow to get there. So that's the x-coordinate. So the height we hit, what will that be? Well, that's going to be y of 2/3 root 2, which is minus 5 times 2/3 root 2 plus 15 root 2 times 2/3 root 2. Okay, now something nice will happen here. What's going to happen here? Well, when you plug in 2/3 root 2, you get 30, right? 15 times 2 is 30. Then you have square root 2 times square root 2 is 2, and divide by 3 is 20. So this whole thing is 20. And you're like, whoa, that's amazing. No, it's not, because we picked t, so that 15 root 2 times t is 20. So of course that should be 20. Okay, great. By the way, I forgot to square that. All right, double check, right? Small mistakes. Small mistakes cost you big points. Okay, all right, now 20. And then we have minus 5. And let's be careful here. We're going to have 2 squared is 4. Square root of 2 squared is 2. And then 3 squared is 9. Okay, so that's 5 times 4 times 2. That's 40 divided by 9. So it's 20 minus 40 ninths. And 20 minus 40 ninths meters. Okay, so what's our answer? Let's be really clear on the question. We now know that this point right here is at 20 minus 4d over 9. Okay? This part, the target, is at 20. So the question was, how far below the target does the arrow actually hit the wall? So it's not asking you for the height that the arrow hit the wall. It's saying, how far below was it? So how do we find that? It's this part that we subtracted off. 20 subtract off that number, that's how far below we're going to hit. So our answer to part B, what a problem this one is. All right, we are going to be 40 ninths meters below. And so there we go. Now that's about 40 over 9 is about, what, 4.5, which is good. Because 4.5 meters is great. if we had said, oh, we're going to hit negative 80 meters below, like, whoa, wait, what? We can't go down that low. But okay, that's a reasonable answer. Maybe. Long problem, right? It really tests your physics, which for me is hard. I haven't done physics in a long time. My goodness, I wonder what all the new stuff is going on these days. But all right, last problem, number 6. Okay, suppose that r of t is t cubed minus 2t, t squared plus t minus 3, 2t squared minus 4t, and it traces the path of a spaceship at time t. They love spaceship problems. Spaceship problems or particle problems, it's all the same thing. Things moving in 3 dimensions. Find an equation for the spaceship's osculating plane. It's the plane containing the velocity and acceleration vectors when time equals 1. All right, so we have a time. Now, remember, we're looking for what? A plane. So we have to find some things. So we're going to write down for reference r of t. That's t cubed minus 2t, t squared plus t minus 3, 2t squared minus 4t. And take the derivative, r prime of t. And the thing is, the derivatives aren't hard. There's just a derivative in each slot. So these really are like Calc 1 problems. Oh, Calc 1. We were so innocent back then. So the thing is, you just have to do it 3 times. So, okay, so I took r t, r prime t, r double prime t. So we have, recapping, t cubed minus 2t, t squared plus t minus 3, 2t squared minus 4t. r prime, 3t squared minus 2, 2t plus 1, 4t minus 4. For r double prime, 6t, 2, 4. All right. Now, from here, we're going to plug in 1. Make sure you plug in the right point, because if it says 1 and you plug in 0, everything's wrong. So, all right, so we're plugging in 1. But I'll tell you, true story, mathematicians, they love 2 numbers. They love 0, they love 1. And there's a great rule of thumb. If a mathematician asks a question, the answer is usually either 0, 1, or it's written somewhere nearby, usually on the board. Okay, so plugging in 1. Now the nice thing is, because you're a polynomial, everything 1 to a power is just 1. So just start working on the coefficients. 1 minus 2, negative 1. 1 plus 1 minus 3, negative 1. 2 minus 4, negative 2. Now, what does this correspond to in our osculating plane? This is a point. In other words, it's a location, because if you're an osculating plane, you're a plane. Planes need locations to nail them down. R prime of 1. All right, so again, coefficients. 3 minus 2, 1. 2 plus 1, 3. 4 minus 4, 0. All right, now this part right here, this is a vector. It's the velocity vector, but it's a vector in the plane. R double prime. Okay, plug in 1. R double prime of 1. We get 6, 2, 4. Oh, those are pretty easy coefficients to work with. Okay, and what is this? It's the acceleration vector. But the key thing is it's a vector. It's a vector in the plane. And now we say, oh, hey, we have 2 vectors in our plane. Well, that's great. If we have 2 vectors in the plane, we can make our normal. And that's what we really need if we're looking for the equation of a plane. And we are, because it says, find an equation for the osculating plane. Okay, 1, 3, 0 across 6, 2, 4. All right, so we're going to set it up. I, J, K. Now, you might be saying, oh, Steve, couldn't I pull out a 2? Yeah, you could have, but oh well. Retrospect is always very useful, but okay, we'll do that later. I times 3 times 4, 12i. J times 0 times 6, 0j. K times 1 times 2, 2k. 6 times 3 times k, 18k, but we're going to subtract it. 2 times 0 times I, 0i, but we're going to subtract it. 4 times 1 times j, 4j, but we're going to subtract it. So that gives us 12 minus 4, and here minus 16. And I'm going to go ahead and pull out a 4, because everything's a multiple of 4. 4 times 3 minus 1, minus 4. Now, I'm going to pause and say, I want my points. So, check your dot products. 3 minus 3 plus 0, 0, good. 18 minus 2 minus 16, 0, good, right? You can always do a quick check to see, hey, is the cross product perpendicular to what I started with? And if it isn't, mistakes were made. And if it is, you're probably 99% of the time good to go. All right, now we're almost done. Here are our coefficients for our plane. So we're almost to the point, almost done, I promise. So what do we have? We have 3x minus y minus 4z equals something. There's something here. And the question is, what's in the box? What's in the box? That's where the point comes in, remember? So we got to plug this point in. Minus 1, minus 1, minus 2. So minus 3, right? 3 times minus 1. Plus 1. Minus minus 1. And then plus 8. Minus 4 times minus 2. And that becomes 9 minus 6, which is 6. That's what goes in the box. So our final answer is 3x minus y minus 4z equals 6. And we're done. Drop the pen. Life is good. And hope you enjoyed it. Hope you do well. See you again. Bye.